Great, thanks. Hi, everyone. I know everyone's probably pretty excited to get to lunch, so thank you very much for bearing with me as we've run a little bit over time. I'm here today mainly to advertise a recent archive preprint by myself and my supervisor, David Savak, where we've derived a series of bounds placing fundamental limits on the performance of collective motor-driven transport systems. So within the cells of living organisms, various important cargo like vesicles, organelles, and even chromosomes are transported by motor proteins like kinesin and myosin, which consume chemical energy in order to take directed forward steps against loads. And one of my favorite features about these motor proteins is that they work collectively to transport cargo with widely varying numbers of motors connected to a single cargo in different settings. So to give you some examples, for kinesin motors pulling small vesicles, you might find 1 to 10 motor proteins per cargo. For myosin motors sliding actin filaments within muscle tissue, you might find about 100 motor proteins in a single actin filament. And for kinesin pulling large organelles like mitochondria, experiments have found more than 200 motor proteins attached to a single cargo. So we really have like a large number of kind of identical small components that are coming together to form a large collective system to achieve directed transport. Now when we think about these systems, if we want to optimize their performance, some desirable characteristics for these transport systems is that they be fast, so a fast directed transport. We want them to be precise, so get the cargo a specific amount of distance in a given amount of time. We want them to consume as little power as possible, or another way of putting that is we want them to be highly efficient, so achieving as much bang for their buck in terms of energy consumption as possible. So the question we set out to answer here is what kind of fundamental limits constrain the performance of these systems? So if you have a collection of components, motors and cargo that you can put together in any way you want, what is the best you can do? What is the best collective transport system you can construct? So to answer this question, we turned to mathematical models of these kinds of systems. So if we think about the simplest model for a motor cargo system, you can consider a single diffusive cargo coupled to n motor proteins in one dimension. Each motor protein can be characterized by some bare diffusivity as well as a driving force due to its chemical dynamics. And then the different components of the system are coupled together via some conservative potential, which can in general include terms for things like coupling between the motors and cargo, interactions between the different motors. You can imagine they might kind of bump into each other if they try to pass each other. And of course, each motor can have some periodic energy landscape due to the interactions with the substrate it walks along. So in general, you might have features like metastable states or energy barriers within the motor landscape. And as we all heard in Yannick's talk, fluctuations dominate for these kind of small systems. So we model the dynamics of the system using multipartite overdamped Langevin dynamics. Now, for multipartite stochastic dynamics, the theoretical framework of stochastic thermodynamics allows us to write down an expression for the total entropy production of this collective system in terms of a sum of terms from each system which are proportional to the ensemble averaged squared local mean velocity. Now looking at this functional form for the entropy production, we noticed that we could apply Yensen's inequality to each of the terms in this sum. And Yensen's inequality, for those who don't know, tells you that the average of a function squared is always greater than or equal to the square of the average of a given function. Now applying Yensen's inequality to the expression for the entropy production, we derive what we call the Yensen lower bound on the total entropy production rate for the system, where we have the total entropy production rate of the system lower bounded by the mean velocity of the collective transport system squared divided by what we call the bare collective diffusivity, which is a function of all the different bare diffusivities of each of the components making up the collective system. Now, for those of you more familiar with stochastic thermodynamics, this might look a lot like the famous thermodynamic uncertainty relation. And indeed, it is very similar, albeit with the effective diffusion coefficient that comes into the thermodynamic uncertainty relation replaced by this bare collective diffusivity. And in fact, for many kind of physiological parameter values, we find that the Yensen bound is tighter than the thermodynamic uncertainty relation. So directly from this Yensen bound in the entropy production follows a series of bounds on specific performance metrics of these kinds of systems. So in particular, we can derive an upper bound on the mean velocity of these systems, an upper bound on the Stokes efficiency, which is a way of quantifying the efficiency of a system which only does work moving against viscous drag forces. And we can define a lower bound on the coefficient of variation, which quantifies the precision of these systems. In fact, it's the standard deviation over the mean of the distance the system moves in a given amount of time. And I'll highlight that these bounds are totally independent of how all the different components of the system are connected together. They only depend on bare properties of the subsystems, of the components in isolation. Now, to extend these results, when all the motors in the system are identical, which is often the case in real biological systems, so identical driving forces and bare diffusivities, but still potentially different couplings to each other and the cargo, we can derive Pareto frontiers, which constrain combinations of two different performance metrics. So in particular, we get an inequality constraining combinations of the Stokes efficiency and mean velocity, as well as an inequality constraining components of the total chemical power consumption and the mean velocity. So let me just explore some of these results with a very simple example system to illustrate some of these ideas. So in particular, we consider two identical motors with identical driving forces and sinusoidal periodic energy landscapes, quadratic coupling to the cargo, and no motor-motor interactions. So this figure gives you an idea of what the dynamics of this system looks like. And for the different curves, let's see, can I make this work? Yes. So for the blue to red, as we go from blue to red, the height of the energy barriers in the sinusoidal energy landscape of the motors increases. So and you can see as that changes, we go from kind of continuous motion to more, the motors get closer and closer to taking discrete steps as they move. And just for reference, we think kinesin motors are somewhere around the orange curve in this figure. So we can use this model to explore the Pareto frontiers we've derived. So again, our predicted Pareto frontier is the black dashed line here for Stokes efficiency and mean velocity. And generating different performance trade-off curves from this model for different parameter values, we find that all these curves lie below the predicted Pareto frontier. And in particular, an interesting result is that as we increase the height of the energy barriers, so going from the blue curve towards the dark purple curve, we see that the system gets farther and farther away from the theoretical Pareto frontier. And just to show you, we see the same results for the other Pareto frontier we derived comparing power consumption and mean velocity. So that really gives us an idea of how these systems can potentially achieve optimal performance values by minimizing the energy barriers in the motor landscapes. Finally, I'll briefly show you some comparison to some experimental data rather than some numerical simulations. So on the figure up here, we have efficiency and velocity measurements for myosin motor systems from a handful of different animal muscle tissues. Like some of these data points are chicken heart and I think lizard forearm and different animal muscle tissues like that. And we see that for a maximum velocity of about 12 micrometers per second, which is roughly what we think it is for animal muscle myosin. This experimental data is indeed constrained by our theoretical Pareto frontier, and it's pretty close, but doesn't quite reach the theoretical limit on performance. So with that, to summarize, we've derived a Yensen bound on the entropy production, which holds quite generally for a broad class of collective transport systems. And this implies new bounds on single performance metrics like velocity, efficiency, and precision. For identical motors, which is often the case in relevant biological systems, we get a series of Pareto frontiers, which constrain combinations of two performance metrics. We show a simple model which can saturate these bounds of frontiers, giving us ideas of what kind of design principles this implies. And finally, of course, this seems to be consistent with experimental findings for myosin. So with that, I'll thank everyone who helped to fund this work, as well as all the members of the Savant group, and especially my supervisor, David. And if you're interested in learning more, please check out our archive preprint. There's lots more on this. So with that, thanks, and happy to answer any questions.